Hi, Weather and Forecasting, Module 2, Part 2. We're going to start talking about causes of seasons and our actual Earth-Sun relationship. So the Earth takes about 365.25 days to rotate itself around the Sun. This is why every 4 years we have a leap year day, and that is to make up for the 0.25 that takes place to actually make it around the Sun. So every 4 years we make up that 0.25 in our numbering. The reason for seasons is not the proximity to the Sun, so it's not how close we are at a given time of year, it's the angle of sunlight reaching the Earth. So the reason why we will have a warm season and a cold season has to do with the direct angle of sunlight, how much sunlight is directly hitting the Earth's surface at any given time of year. Which brings us to the concept that in what we would consider our winter months, we're actually in proximity, the Earth itself is closer to the Sun, where which we would consider in the Northern Hemisphere our summer months, July 4th, we're in proximity actually further from the Sun. The other thing to make note of is that we rotate around the Sun, we being the Earth, rotates around the Sun in an elliptical plane. Which brings us to the Earth itself. So the Earth itself is rotating on a point of axis. The axis of rotation is actually 23.5 degrees from the northernmost plane. And so we're actually tilted. Our Earth is perpendicular to its axis relative to sunlight. This means that as we're rotating the Sun, we're rotating at a 23.5 degree angle. So our point of rotation is here and here, not here and here, not completely vertical. We're on this lovely axis here. So we're rotating around on this angle in our rotation set. The Earth itself takes 24 hours to spin around in a complete circle. Because of our axis of rotation, because we are on this lovely angle that we're rotating on, this 23.5 degree angle, it means that sunlight will hit more directly, or at 90 degrees, different spots on the Earth's surface. So as you can see from this picture, when we're tilted and sunlight is able to penetrate the northern hemisphere most directly, we would consider it our northern hemisphere warm months, our summer, right? On the other hand, when the tilt is tilted in the northern hemisphere away and in the southern hemisphere towards the sunlight's hitting most directly in the southern hemisphere, and that would give us our winter in the northern hemisphere and the southern hemisphere their summer. On the other hand, when the tilt doesn't matter, we are in our lovely fall and spring seasons, and they are known as our equinoxes. So that brings us to, where is the sunlight hitting at 90 degrees? Oh, I don't want to go there yet. Sorry. Here we go. Where is the sunlight hitting at 90 degrees? And so the 90 degree angle of sunlight on the equinoxes is exactly at the equator. So they are at 0. So equinox, equator, 0 degrees latitude. On the other hand, in what we would consider our December solstice, the most direct sunlight is hitting in the southern hemisphere at 23.5 degrees south latitude. On the other hand, in the northern hemisphere, when we talk about our summer months, receives the most direct angle of sunlight at 23.5 degrees, so 90 degree angle of sunlight, 23.5 degrees north during our June solstice time of year. This brings us to seasonality, which goes into this lovely picture that's just talking about how if I was to change the angle of sunlight, if I was to change the Earth's rotation, I would change the angle of sunlight as it spun. So in this lovely example, they're trying to show you that if we tilted the Earth completely on its side, and I set 90 degree angles, my equinoxes would still be during my fall and spring type times of year, and they would still hit the equator equally. On the other hand, if I tilted my Earth-Sun angle completely, So I was tilting it on its side, on its rotational plane. It would hit the North Pole during my what I would consider summer months, and my southern hemisphere would be plunged in absolute darkness. And in the winter months, I would plunge my northern hemisphere in absolute darkness, and my southern hemisphere would receive 90-degree angle of sunlight directly on the South Pole. And so this is just giving you an example of how that tilt works on a more extreme level to try to get you to really have a full and complete understanding of what we're talking about in our times of year. Now, you're going to be experimenting a little bit with winter and summer solstices, and you'll actually be doing this in your lab activity with the course. So I won't go into it with too much detail, but obviously if you have questions or confusion on this sort of thing, please post them into the conversation, into the discussion modules. Just showing you winter, summer solstice, Earth's angle. This has to do with the angles of sunlight. So winter and summer solstice right here, you can see that our most direct sunlight is actually in our northern hemisphere, which means that this is considered the circle of illumination, this little line here that I'm using my arrow to outline. That means that anything at 66.5 degrees north latitude up is plunged into 24 hours of daylight in this image. So this whole area will never pass into the circle of illumination and will have 24 hours of sunlight. Everything from here on will have some darkness hours, but for the most part, the majority of their 24-hour rotation will be daylight and have some darkness. You can see that my 90-degree angle of sunlight is right here at 23.5 degrees north latitude. And you can see that the amount of sunlight reaching the southern hemisphere is decreased. And then right here at 66.5 degrees south latitude, you can see that the circle of illumination is plunging everything on this point of the circle. This is my Antarctic circle, Arctic circle, Antarctic circle. It's plunging everything into 24-hour darkness. So everything at 66.5 degrees all the way to the actual southern pole is in 24 hours darkness. The opposite occurs in the December months, where everything at 66.5 degrees north latitude to the North Pole itself is plunged into 24-hour darkness at December solstice, which could be the 20th or 21st. And everybody in the northern hemisphere will have less daylight hours, more nighttime hours, right? More darkness than light. And everybody in the southern hemisphere is getting more light than darkness. Everybody in the Antarctic circle of illumination here is in 24-hour sunlight down here. And the sun is hitting the Earth's surface at a 90-degree angle at 23.5 degrees south. Equinoxes are even. So my tilt, the Earth's tilt on its rotational plane, doesn't matter on these at the equinox points of year. And that's why everyone receives 12 hours of nighttime and 12 hours of daytime. And the most direct form of sunlight is hitting most directly at 90-degree angle at the equator itself. And this happens at the equator 2 times a year. And so these are my equinoxes, my fall equinox or my autumnal equinox, and my spring equinox, my vernal equinox. Talking about solar angle, obviously if I take a flashlight and I was to shine it directly down at a 90-degree angle, so in picture A is a 90-degree angle, my sunbeam, my light beam, will be very concentrated and have a lot more energy to it than if I take that angle of light and I actually turn it to a degree so that it's on a plane or an angle, and then my light has to be spread out more, so it's more spread out, and the light itself is less intense. So this has to do with intensity of the amount of energy received at any given spot. So on that note, I'm going to pick up with part 3 of our video set.